Hi everybody, today we're going to be talking about section 7.3, which is about thermal inversion, which is sometimes called temperature inversion. The learning objective for today is that you can describe thermal inversion and its relationship with pollution. Some of the essential knowledge that you're going to gain is what occurs during thermal inversion and how this is going to trap pollution close to the surface of Earth. So before we start talking about the thermal inversion event, it's important that you understand what's known as an urban heat island, because that's going to relate to how we are going to be getting this thermal inversion occurring, especially in urban areas. So urban areas are typically going to have higher surface and air temperatures than surrounding suburban and rural areas, which you can see on the graph here. In the downtown urban areas, we're going to have higher temperatures than in these rural and suburban areas. And that's because, first of all, of a lower albedo. So the concrete and the asphalt is going to absorb more of sun's energy, which means it's not going to reflect as much, which is what the albedo is. So they're going to be absorbing more than these areas with vegetation in rural areas. Now, the absorbed sunlight is going to be giving off as infrared radiation or heat. So we're going to be absorbing all of that sunlight, and then that's going to release heat after it has been absorbed, which is going to contribute to these higher temperatures. So what we're going to have here is the sunshine, and it's going to be coming and it's going to be hitting urban areas and rural areas. Now, this is going to lead to that heat that's going to be reflected. Now, another thing that comes into play is this evapotranspiration, which, if you remember all the way from Unit 1 when we talked about that, evapotranspiration is where we have water evaporating from the surfaces, and then also transpiration that occurs where plants are going to be transpiring from their leaves. So all of this evaporation from the surface and from the plant's leaves is going to carry heat away from the surface in the atmosphere. However, in urban areas, we are going to have less of that evapotranspiration. And so in rural and suburban areas where you have more vegetation, it's going to help cool it off because you're releasing some of that, as we see with our little clouds and blue arrows in the diagram in the rural area. Now, because we don't have so much of that, you're going to end up having a lot of that heat more trapped in these areas, which again is going to contribute to these higher temperatures in urban areas. And these higher temperatures in urban areas are what is known as a heat island effect. So now we're going to look at thermal inversion. So normally, the way that the atmosphere works is that it's warmest at Earth's surface, and then it cools as the altitude rises. And if you remember from our Unit 4 stuff, that's because of the fact that the Earth's radiation, or the sun's radiation is going to come down to Earth, and Earth is going to absorb it. And so it's going to be warmer close to the Earth's surface. Typically, that's how it goes. Now, because warm air rises, this causes air convection. Think back to Unit 4 with our Hadley cells and the warm air rising and the convections that are occurred from that. Now, this convection and the movement of the air is going to carry air pollutants away from Earth's surface and distribute them higher into the atmosphere. So if we've got this pollution, these air pollutants, the smog, it's going to rise with the warm air, and it's going to get dispersed up into the atmosphere. Now, during a thermal inversion, this process gets messed up. What happens is there's a cooler air mass becomes trapped near the Earth's surface. So it's going to invert the normal gradient. Now, this can be caused from a few different things. Specifically in coastal areas, like this cold air can come off of the water. It can also be due to just wind movement and stuff like that. So it could be from a warm front moving in over it. It could be also in urban areas due to the hot urban surfaces when they cool overnight while the infrared radiation is still being released from what was absorbed during the day. So there's a few different things that can cause it, but ultimately it's going to lead to the fact that we have this cooler air trapped under the warmer air. And you've got the air pollutants are also going to be trapped there. Now, the problem is, remember that it's warm air that rises, but this is going to be cooler air. So it's not really going to be rising, which means even though you have all these air pollutants being released down at this level, that cool air isn't going to be rising like the warm air does. So it's going to be trapped beneath this warm air layer, which means convection is not going to be occurring. We're not going to get that movement of air. So the pollutants are not carried up and away. They get stuck right here. And so you're going to have higher levels of air pollutants and smog because it's not being dispersed up throughout the atmosphere. Now, the effects of a thermal inversion. This image here is a photo of Los Angeles, which is going to give you a pretty extreme view of what can actually happen with these thermal inversions. Now, one thing it's important to mention that I didn't mention on the last slide, but just be aware, is that actually mountain regions can cause these to be even worse of an inversion event, because the mountains, you're not going to have as much wind coming through to just like push everything out and move it around. So that's one of the reasons why LA has these thermal inversions occur somewhat frequently, because they also have mountains right by there, and so it gets trapped and you have even less movement, so the thermal inversion event can stick around for longer. So what's going to happen? The effects of these thermal inversions. So first of all, you're going to have the air pollutants like smog, particulate matter, ozone, the SOx and the NOx are going to be trapped closer to Earth. So Los Angeles is this photo example of where this is going to occur. Now, what this can lead to is respiratory irritation. Asthma is going to flare up, which can lead to more hospitalizations. You can have worsening COPD. You can have emphysema. It can eventually actually lead to death. There have been some pretty extreme versions before in like the 30s and 40s in England and in New York, where we got crazy levels of this inversion for days at a time, and people actually died from it. Thanks to the EPA, we don't have as much of that extreme levels going on anymore, but it definitely leads to asthma flare-ups and hospitalization, worsening COPD, emphysema, which ultimately can lead to death for some people. It's also going to decrease tourism revenue. People sometimes don't want to visit LA because of the smog that they have, and so that can have an impact on tourism revenue, especially in times where they're having an event. People might have had a trip planned, and then they might decide to not do that trip if the air level quality is bad. Another problem that it's going to lead to is decreased photosynthetic rate, which is going to be bad for plants, and especially is going to be bad if there's any sort of farming and agriculture nearby, because their plants are not going to be doing as well. All right, so this is going to be your practice FRQ for 7.3, where you're going to practice the suggested skill of explaining how environmental concepts and processes are represented by a visual representation. So in this picture here, we've got normal conditions, and then what happens when we have a thermal inversion, also called a temperature inversion. So what I want you to do is to explain what the arrows in each diagram illustrate about the impacts of a temperature inversion on air pollutants, such as smog. That'll be your practice FRQ for 7.3, and those were your notes on 7.3 about thermal inversions.